Here is a combined summary of pages 1 and 2. Large language models based on transformers have achieved significant success, but understanding their internal mechanisms is crucial to improve their reliability and mitigate failure cases. This study focuses on how transformers balance global and in-context knowledge, using a synthetic setup where tokens are generated from either global or context-specific bigram distributions. The authors introduce a simplified two-layered transformer architecture, freezing some layers at random initialization, to study the role of attention and feed-forward mechanisms in learning. They view weight matrices as associative memories, storing input-output or key-value pairs of embeddings through their outer products. The authors provide a detailed empirical study of the training dynamics, measuring how quickly each weight matrix learns to behave as the desired associative memory. They find that the model first learns global bigrams and then develops an induction head mechanism for in-context bigrams, which appears to be ubiquitous in transformer language models. Theoretical insights on the top-down learning process are provided through population gradient dynamics, showing how a few top-down gradient steps on the population loss can recover the desired associative memories by finding signal in noisy inputs. The study highlights the importance of understanding how transformers develop their capabilities during training, particularly in the context of in-context learning. The authors propose a new synthetic setup to study global versus in-context learning and provide contributions to the field, including viewing weight matrices as associative memories and empirically studying the training dynamics. The study is related to previous works on mechanistic interpretability, memory and neural networks, and the use of random vectors for storing memories. The approach to probing based on memory recall is related to techniques in previous studies, but motivated differently. Future research directions include optimization algorithms, data preprocessing and selection, interpretability, fine-tuning, and model editing. The research paper discusses the induction head mechanism in transformers, which enables in-context prediction. It begins with the induction head mechanism, where a two-layer mechanism predicts the next token based on context. This involves a previous token head and an induction head, which attends to the output of the previous token head. The paper then explains the attention block, feed-forward block, and unembedding process used in the transformer. It highlights the importance of residual connections and the simplicity of the setup for understanding the induction head mechanism. The paper also presents experimental results on synthetic data, showing that the model achieves high accuracy in predicting output tokens after the first occurrence of a trigger token. The attention maps visualized in Figure 2 demonstrate the model's learning of the induction head mechanism, particularly for fixed and random triggers. The study suggests the presence of a memory in the attention layer for fixed triggers and the ability to disambiguate between in-context and global predictions for random triggers. In this section, we present an associative memory viewpoint on transformers, where weight matrices behave as associative memories storing pairs of embeddings as a weighted sum of their outer products. We introduce a simplified transformer model with fixed random embeddings to understand learning dynamics. The model freezes input, output, and positional embeddings throughout training, and fixes the key and query matrices to their random initialization. It trains the output embeddings to predict the next token. The architecture includes a single linear feed-forward layer after the second attention block, which is responsible for learning global bigram distributions. We show how this model can solve the synthetic bigram problem by ignoring certain elements of the set and focusing on positional embeddings. The induction head mechanism matches a token to the previous tokens using positional embeddings and remaps the input token to the corresponding output token. The global bigram statistics are encoded in the feed-forward layer. The research paper explores the learning dynamics of transformers, focusing on the emergence of the induction head via top-down learning. The authors examine how the model trades off predictions from the induction head and the feed-forward layer, highlighting the importance of choosing between these components depending on context. They simplify the transformer architecture to better understand the role of each matrix, demonstrating that the induction head is preferred unless its output agrees with top predictions from the global bigram. The empirical study involves training models on synthetic bigram data, using Minibotch SGD with momentum and fixed hyperparameters. The authors employ memory recall probes to check whether individual matrices have learned desired associative memories. They also measure the average KL divergence between the predicted softmax distribution and the global bigram distribution. The results show that training key-query matrices does not lead to learning unless the output matrix W20 is learned first. W20 can learn correct associations even when trained alone with key-value matrices at random initialization, resembling a bag-of-words model. The associations in W20 enable learning key-query matrices that focus attention on relevant tokens, eventually recovering the desired induction head behavior. The authors observe that W2K is easier to learn when W1K is frozen, and W1K stores initial context positions much faster than late positions. They also find that the global bigram statistics are learned more quickly than the induction head, with a tension between W20 and WF later in training. The role of the data distribution is also examined, with changes such as reducing the number of triggers, using rare fixed triggers, or using random triggers slowing down in-context learning. The authors hypothesize that these changes affect the speed of learning W20 and key-query matrices. The findings provide a fine-grained understanding of the learning dynamics of induction heads, shedding light on the importance of top-down learning and the interplay between different components in the transformer architecture. In the context of transformer models, this research paper delves into the question of how these models develop in-context learning abilities. The study focuses on a simplified setup that allows for a detailed understanding of the model and its training dynamics. The paper highlights the importance of understanding how gradients near initialization can lead to the emergence of induction heads, which are crucial for contextual learning in transformers. The authors demonstrate that when using a simplified setup, transformers can learn in-context abilities through gradient dynamics. They show that after a few gradient steps, the model can develop an induction head mechanism that enables contextual learning. This is achieved by leveraging the associative memory property inherent in transformer models, where gradients at initialization can lead to the formation of associative memories between input and output tokens. The paper also explores the role of data-distributional effects on in-context learning. It demonstrates that training with a uniform output token distribution can lead to better generalization than training with bigram distributions. This is because the uniform distribution encourages the model to learn more diverse associations between input and output tokens, which results in better generalization across different data distributions. Moreover, the study provides theoretical insights on learning the induction head mechanism via sequential gradient steps. The authors prove that after initializing the key-value matrix and output matrix, a few gradient steps can learn the desired associative memory that focuses the attention on correct triggers. This result is supported by numerical experiments verifying the correctness of this process for finite data and dimension. Finally, the paper discusses potential avenues for future research, including understanding how transformers leverage more complex aspects such as nonlinear feed-forward layers, factorized key-query and value output matrices, and learning embeddings that are adapted to the data. These aspects are crucial for understanding how transformers perform in richer settings beyond the simplified setup considered in this study. The research presented on pages 11 and 12 delves into various aspects of machine learning, focusing on topics such as neural networks, attention mechanisms, and transformer circuits. It discusses the high-dimensional asymptotics of feature learning, how one gradient step improves representation, and the significance of gradient descent in neural networks. The pages also explore the concept of implicit regularization in matrix factorization and its implications. Additionally, they touch upon the neural tangent kernel, convergence, and generalization in neural networks. The discussion on transformer circuits highlights their ability to learn and generalize, with a focus on the mathematical framework and its applications. The summary concludes by mentioning the importance of understanding the underlying mechanisms of transformer circuits and their role in in-context learning. Here is a combined summary of pages 13 and 14 of the research paper. The authors provide a comprehensive list of references related to transformers, attention mechanisms, and associative memories. These references cover various aspects of transformer architecture, including their strengths and limitations, as well as their applications in natural language processing and few-shot learning. The authors then delve into the properties of associative memories based on outer products of random Gaussian embeddings. They consider embeddings UK element of road with I. I, D, Gaussian n, 0, 1, d, entries and recall several facts about these embeddings. Specifically, they show that the norm of UK is approximately 1, and that the dot product of two different embeddings UK and UJ is 1 square root d. They also demonstrate that if W is a Gaussian random matrix, then for any fixed x, the norm of Wx is approximately equal to the norm of x. Furthermore, they show that if x is a normalized Gaussian embedding, then Wx is nearly orthogonal to x. The authors then discuss the remapping properties of these embeddings, including the norm and near orthogonality properties. They demonstrate that these properties hold with high probability, and that they are essential for ensuring correct associations in associative memories. However, they acknowledge that a precise analysis of these properties is an important direction for future work. Finally, the authors provide additional theoretical insights on gradient dynamics, including details on an illustrative example, derivations of gradients with respect to key-query matrices at initialization, and a study of how the induction head mechanism may develop in a simplified setup. They consider a specific example where the goal is to predict y from x equals y plus pt, where pt is a positional embedding at a random position t. They analyze the matrix obtained after one population gradient step with step size eta, starting from an initialization w0 equals 0. Here is a combined summary of pages 15 and 16 of the research paper. The authors derive expressions for population gradients of attention key-query matrices at zero initialization, which leads to associative memories. They begin by analyzing the gradient of the second attention layer with respect to the key-query matrix W2, noting that random initialization behaves similarly to zero initialization. The gradient is given by equation 13, which involves the cross-entropy loss and softmax functions. Next, they consider the gradient with respect to the key-query matrix W1 of the first attention layer, linearizing the second layer attention around W2 equals 0. The gradient is given by equation 14, which involves the linearization of the softmax and the key-query matrices. The authors then proceed to analyze the training dynamics of the induction head mechanism, assuming a simplified setup with a single trigger token and uniform distributions for the attention weights. They consider a loss function that only considers sequences of length t, where the last input is the second occurrence of the trigger token, and the label y is the corresponding output token. In this setup, they show that the expected loss is dominated by trigger tokens, leading to the recovery of bigram statistics. They then focus on the learning of W20, W2k, and W1k in a top-down order, considering zero initialization and a single gradient step. The authors note that random initialization leads to a remapping of input embeddings that is near orthogonal to any output embedding, which is similar to the setup of lemma 1. This leads to the recovery of bigram statistics when the dimension is large enough, as shown empirically in section 5. Overall, the authors provide a detailed analysis of the gradients of attention key-query matrices and the training dynamics of the induction head mechanism, highlighting the importance of associative memories and bigram statistics in the learning process. Here is the combined summary of pages 17 and 18 of the research paper. The authors analyze the behavior of the model after one gradient step on the weights W20 and W2k. They start by rewriting the logit predictions in terms of the random sequence Z1, t and the noise vector epsilon t. The gradient step on W20 yields an update rule that depends on the expected value of the embeddings we, ZTO, and the attention output phi1 we, ZTO. This update rule can be simplified by assuming near ortho-normal embeddings, which leads to a behavior that matches the desired associative memory. However, this update rule also introduces spurious associations due to the output of the first layer attention, which may be cleaned up once the attention layers start focusing on the correct tokens. Despite the recovery of useful associations, the predictions with this estimate W20 are still near random due to the bag of words setup with average attention. The authors then analyze the learning of W2k, assuming that W20 is as in the previous equation. The predictions are essentially random, and after one gradient step on W2k, the update rule depends on the expected value of the inputs to the second attention layer xt. By considering a simplified architecture and using the fact that trigger tokens are sampled uniformly, the update rule can be rewritten in terms of the expected value of it, k, which depends on the embeddings wu, k, and the attention output phi2xt, 0. By using the fact that wu, k, phi2xt, 0 approximately equals alpha 1, zt equals k, and xt, 0 equals w, q, plus pt. The update rule for W2k can be simplified, and it is shown that the term increment k, j carries the desired signal for the appropriate induction head associative memory, while the terms increment qk, j and increment rk, j are negligible for large n. The research paper discusses the development of an associative memory model, focusing on the control of increment o and increment q terms. It begins by explaining the near-ord anormality of the matrix, which allows for the approximation of ACK, J, I. The paper then distinguishes between several cases, including when J is not equal to K, and when J equals K. For the latter, it derives an expression for ACK, J, I based on the trigger token's position. The authors also discuss the control of increment R terms, providing a crude bound for the difference between the expected values of the trigger token given Y and Q. They conclude that, up to some spurious positional embeddings, the model behaves as the desired associative memory when n is large enough. The paper then moves on to learning W1k, assuming W20 and W2k have learned the correct associations. It considers one gradient step away from zero initialization on W1k and discusses the simplified architecture where the first layer attention only uses positional embeddings in the keyquery matrix. The paper discusses the behavior of an associative memory model, focusing on the previous token head behavior. It derives an expression for the expected value of a specific quantity, W1, which approximates the desired behavior when the number of tokens, n, is large. This involves the use of trigger tokens and their probability. The model's behavior is analyzed through various equations and algorithms, including the calculation of expected values and their derivatives. The paper also presents proofs for several lemmas, which are crucial for understanding the model's behavior and the convergence of the softmax. These proofs involve the cross-entropy loss and its derivatives, demonstrating how the gradient of the loss at the model's parameters affects the parameters themselves. The discussion highlights the importance of the model's architecture and the role of keys and values in the attention mechanism. Overall, the paper provides a detailed technical explanation of the model's behavior and its mathematical foundations. Here is a combined summary of pages 23 and 24 of the research paper. The authors present the proof of lemma 5, which involves the linearization of the second layer's softmax around 0. The output of the first attention layer is denoted as ZT, and the linearization takes the form of a Taylor series expansion. The gradient of the loss function with respect to the model parameters is derived, and it is shown to consist of two terms. The first term represents the contribution from the output of the first attention layer, while the second term represents the contribution from the output of the second attention layer. The authors then discuss how their memory viewpoint extends to more complex transformer architectures, which typically involve multiple heads and layers. They introduce the concept of factorizations, where the weight matrices are decomposed into products of matrices. This allows for a low-rank bottleneck, which is common in practice. The authors show that a similar associative memory can be achieved with the factorization W equals D, 2D, UV, where U and V are matrices with specific properties. The authors also discuss the role of layer normalization in transformers. They show that layer normalization can be seen as an operation that normalizes the input or output of a given block, and it is typically used to improve training stability. The authors derive the gradients of the loss function with respect to the model parameters, taking into account the layer normalization operation. The key insight from this section is that the author's memory viewpoint can be extended to more complex transformer architectures, and that layer normalization plays a crucial role in stabilizing the training process. The authors provide a detailed mathematical treatment of the topic, including the derivation of gradients and the analysis of the associative memory properties. Here is a combined summary of pages 25 and 26 of the research paper. The authors illustrate how layer normalization in neural networks projects updates onto the orthogonal of the input embedding direction, preventing excessive norm growth and encouraging similar weighting of frequent and infrequent tokens in the final memory. This mechanism only becomes significant later in training, as initially, the input embedding is nearly orthogonal to the update direction. The authors also discuss the role of multi-layer perceptron (MLP) blocks in encoding associations between input and output embeddings. These blocks can filter out noise arising from near orthogonality, leading to additional storage capacity at the cost of increased computation. MLP layers can also encode many-to-many associations, which is useful when considering multiple embeddings in the residual stream. The authors extend their view of weights as associative memories to multiple heads and layers, but note that this introduces redundancy, making it challenging to identify which layer or head will learn specific associations. They highlight the importance of causal identification techniques, such as mediation analysis, for interpretability. The authors proceed to provide experiment details, including the computing setup, hyperparameters, and additional results. They present memory recall probes for different settings, showcasing the evolution of associative memories during training. The probes demonstrate that associative memories for the induction head are slower to learn when using few triggers, rare fixed triggers, or random triggers. The authors also visualize the weights of the different matrices after training, illustrating the learned associative memories. These visualizations provide insight into how the neural network encodes associations between input and output embeddings, enabling the network to perform tasks such as factual recall. Overall, the authors provide a detailed analysis of the mechanisms underlying neural networks, highlighting the importance of layer normalization, MLP blocks, and associative memories in encoding complex associations between input and output embeddings. The research discusses the development of associative memories with random embeddings, focusing on the learning of W2 with varying dimensions and the effect of using uniform output tokens. It highlights the importance of dimensionality in achieving faster learning and the benefits of uniform output tokens for better fitting. The study also explores the behavior of the associative memory, visualizing associations and their strengths, and examines the impact of more complex architectures on training dynamics. The results show that higher dimensions lead to faster learning and that using uniform output tokens improves recall accuracy. Additionally, the research touches on the challenges of interpretability in complex models, particularly those with redundant parameters. The findings suggest that the model is identifying the same memory associations even with added complexities, and attention maps reveal difficulties in identifying specific behaviors in multi-head models.